Then, okay. So, welcome back, everyone. I hope you had a good lunch. So, uh, as I promised that right now, the only focus, like I'll just take 20 to 25 minutes and I will tie up some loose ends. As we saw in the last lecture, we saw two frameworks for these like general quantum algorithms. And I promised you that if you look through that survey by Gillian, like you will find that this rabbit hole of general frameworks goes like a lot deeper than what I'm doing here. Right now, I want to give you a small inkling into that rabbit hole by taking the two frameworks that we have considered before. So the tasks are still on board. That's a good thing. So we will consider a framework where we can sort of do all these tasks simultaneously. So we already saw that block encoding cannot do task 2 efficiently. It can. We can do task 2 even with block encoding, but not efficiently. And LCUs actually don't give us a way of thinking about tasks 1 and 3. So right now, we will try looking at something by combining these two frameworks into something that is able to achieve all of these three tasks efficiently. Of course, like modulo the oblivious amplitude amplification routine. So yeah, that's for a later boot camp course. So linear combination of block encoded matrices, which is what we were promised. Now, if you think back to the LCU problem, we needed these two oracle accesses given to us. And we also discussed the motivation behind why these two sort of oracles are natural assumptions to have, right? Now I will take this particular prep state and I will generalize this a little bit. Okay. I hope like by this, like by this time, all of you can sort of recognize what these are, right? They are just unitaries of that form, of the prep form. And here, like one thing I must mention, even though it's not written a little bit clearly, see, y is an m-dimensional vector that we have going on. Okay. The point of this is, so okay, let me ask you the question, because like you guys are trying to understand what's going on. Why was the prep unitary needed in the first place? Create a superposition of a particular form. And huh, in fact, think about this a little more deeply. Take HHL as a concrete example. The B vector, right? The unitary actually implemented B. Like we were trying to do an amplitude encoding of B, right? Now, the problem at hand is, let's say Y is a general m-dimensional vector, right? Complex vector. We shall make use of these two oracles to approximately build up Y. It's going to be pretty straightforward. It's just, so what we say is that PL dagger PR is a beta B epsilon state preparation pair of Y if, okay, I painted myself into a corner over here. Okay. If summation of j equal to 0 to m minus 1, beta, this is Cj, right? Yeah. Cj and Dj. Okay. Dj minus Yj. Let's take a look at this, and this should be pretty obvious, right? What I'm now saying is that PL dagger PR basically gives me a vector that is like an L1 estimate away from Y itself. So its entry wise, like there's a difference, and the difference at most adds up to epsilon. So this, the definition is clear, right? Have a look at the definition once more. And here, like I'm considering that 2 to the B can be greater than M. So anything that exceeds this M, like the mth term, is set to 0 straight away. And only the entries Cj star and Dj are what matters, and scaled by beta, they are at most like some epsilon over M away from the actual entry. So this is what we actually are going for. Immediately you can understand that this state preparation pair, this pair of unitaries, PL dagger and PR, are a generalization of the things that we saw during HHL. For example, if you recall, in HHL we had these two oracles, right? One was a matrix entry oracle and one was a sparse access oracle, right? Now consider that the matrix that I am trying to sort of build up, the A matrix, which is sparse matrix. If I had a pair of these row and column, so let's say PL was a column access oracle where given I could get the superposition over all the column elements, and R, if given the row, I could get a superposition over the row elements. Now, just by constructing a gram matrix out of PL dagger PR, I could get the entire oracle given to me, the entire matrix given to me. So this is what I was actually trying to like tell Jakumar. So that's why the assumption, so I don't remember what assumption number it was, but one of the assumptions said that we had access to these kind of oracles. This is exactly why they are needed. Okay. The second, yeah. So you can think of them as like, uh, okay, just for more context, like just to add to that. So there was a paper by Kerenidis and Prakash in 2016 that actually used oracles of the form p call and p row to build like p row dagger and p call to build these summation of call shiro sort of thing, and this exactly like expanded out gives you the matrix. So summation over call and row. This is based on the QRAM, which is exactly why I did not discuss this. Because to discuss this, I have to discuss QRAMs. That's because of QRAM. And in fact, like the entire point of this Frobenius norm comes into play over here. Because yeah, exactly. So the question that Jayakumar asked in the morning, now you see that it took almost 3 hours to build up to the answer of that question, and even then I cannot answer the question straight away. It's a difficult question to answer. Yeah, Anupam Prakash and Ioannidis Kyriakidis. So, in fact, they gave a straightaway implementation of HHL in this quantum k-means algorithm, which is a very famous application of HHL. Like one of the first applications of HHL was quantum k-means. And what Anupam, another Anupam amongst us, was talking about was this applying these POVM operators, right? There is a technique of applying POVMs using gram matrices. In fact, we saw how to do block encodings of projections, block encodings of density operators. We can also do block encodings of sparse gram matrices. Exactly the same thing is needed. But as uh, Sham, I was thinking Chetan, I got confused. Yeah, sorry. As Sham was pointing out that this, even though it looks like a natural thing to do, implicitly assumes that we have a quantum RAM access given to us. In fact, it assumes something called the QQ RAM. It's a very strong quantum RAM model. Like you load quantumly, you read quantumly. So like it's a very strong quantum RAM model. So I am not going to discuss this, but yeah. No, they actually define the model and they define how to construct block encodings. I don't think they call it block encodings in the original paper, but later papers actually pick up their idea and start calling it block encodings. In fact, in their paper, you would actually recognize the block encoding form that we are seeing right now, but they actually started the idea of block encodings. Kiran and Prakash, if you are interested, you can read the paper. It's a very nice paper. Ah, yeah. Okay. So now that we have this particular form, now we go to the actual theorem. And this theorem is by Low and Chuang. I think this is by Low and Chuang, and then later it was improved by Gillian et al. So Low Chuang 16 and then G plus 19, I think. It will be there in the notes. The actual like the authors will be there in the notes. And the proof of this theorem actually can be done with whatever we saw so far. It's not very hard to do, but it's lengthy. I'll just be talking about the theorem and the implications of the theorem right now. So, okay, just a detour. We saw what the prep state was, right? Now all we are left with is the select state. As long as we have the select and the prep state, we can do a linear combination of things. And block encoding, we already saw what block encodings are. Okay, so let A equal to summation of yj aj j equal to 1 to m bn s qubit operator. Okay, fine. And here ages can be linear operators. We don't care what they are. Like, we are equipped to handle these things now. Okay. Let PL and PR be beta B epsilon 1 SPP for Y. What is Y? No, no. Y is already given, defined in the problem so far. Yeah, no, no. So Y contains, encodes the amplitudes or the weights of this linear combination. That's why. Okay. Yeah. I mean, this is the reason like you get confused. So it's good to take a step back. Okay. Yeah, this is a problem. If this goes down, this goes down, right? I mean, okay. It looks weird, but this is in fact a sort of select operator. It's just a more complicated select operator because now you are condition. So if you take J cross J common, right, this entire thing common, you will see that you are sort of applying a rotation. So you have already seen operators of this form, right? I minus some projector, some state, rho, right? You have already seen things like this. In fact, you have also designed Hamiltonian for Grovers, right? This is exactly a similar kind of select operator. This select operator specially applies a reflection conditioned on JJ, but it's written in this weird form. In fact, this is the easiest form I can write it in. Okay. This should I keep? Yeah. Let the tasks be there. Okay. So can anyone tell me like what is the number of qubits W acts on? Hmm? So this will be B actually. Yeah. So you have S from here. So okay. I should mention what UJs are. UJs are block encodings of ages. And I think you can call them as with epsilon 2 error alpha A epsilon 2. So W is a S plus A plus B qubit operator. S from here, A from here, 2 to the power S. So, yeah. So when I mean S qubit operator, I mean it acts on the Hilbert space, like which is of this dimension. So W is an S plus A plus B qubit operator. Okay. Then, so this carries on here. Then we can implement alpha b, a plus b, alpha beta epsilon 2 plus alpha epsilon 1. This is the theorem. Let's look at the theorem once more. I have a combination of linear operators, a linear combination of generic linear operators, yj, aj. I have a state pair, a beta b epsilon state pair. Now so can anyone spot like what the actual contribution of this theorem is? Like what is the non-trivial part of this theorem? W is so designing this select operator is the non-trivial part. So when you want to put algorithms into this LCU plus block encoding framework, designing these W's is actually where your novelty lies. Now we have a select operator of this particular form, which depends on block encodings of the individual ages. Then given this, we can implement an alpha beta, which is the normal scaling factor that we actually want. So where beta comes from the scaling factor of y itself. So if you can have a state preparation with no error, which is sort of doable in most cases, then you have an alpha a plus b, alpha beta epsilon 2, again beta disappears. So you just have an alpha, just this term remaining, because if this is easy to implement, then we don't require this. This is the most efficient implementation of block encodings of linear combinations of block encodings. Now, another like large homework task for you is try to see if the HHL algorithm can fit into this framework. We have already discussed all the small bits and pieces, right? Quantum phase estimation we can implement as block encodings. The conditional Hamiltonian that we are applying can fall into this particular form because it's just, if you recall, we are just applying summation over tau tau into some Vj, right? Which is my phase estimation operator. So u to the power j, whatever it was. So V tau. This part is just the linear combination of unitaries part. This part is the block encoding part. Try to see, given this theorem, if you can put HHL into this framework. Spoiler alert, yes, you can. I mean, obviously you can. But this is where we conclude our discussion, and we have checked off 1, 2, and 3. In fact, we have managed to go for a fourth task, which is a combination of 1, 2, and 3. So this is where I leave you, like just a short summary of whatever we did throughout the day. We saw, we discussed a problem, the quantum linear systems problem, which is an inherently quantum problem. That is the hardest problem that any efficient quantum algorithm can tackle. It's BQP complete. And we gave an optimal algorithm to tackle that problem. So any algorithm that does much better than the algorithm that we saw, the HHL algorithm, will actually end up showing that BQP equal to P space. We discussed this, right? Then what we started doing was we started breaking the steps of HHL into frameworks. We tried looking at the bigger picture. HHL is nothing but Hamiltonian simulation of the phase estimation of algorithm. Then we looked at how to take this Hamiltonian simulation and put it into the block encoding framework. And then we saw how to take this summation operation in the phase estimation and put it into the LCU framework, which we discussed separately. Then in the last theorem, we are seeing how to combine these two frameworks together. So that's the summary for today. What next is a question that you might have. I would be very happy if you have that. And I have mentioned this several times. What next is qubitization, quantum signal processing, and USBT. These are the next steps. If Sham has time, he can talk to you about little bit about qubitization. I don't know if you have time though. I don't want to put more onto your plate. But the idea now is instead of having these block encodings as any unitaries, I start block encoding into special types of unitaries that are easier to implement. So that is the qubitization framework. The QSP framework actually takes closer look at these ABCD and BCD entries and tries to put everything in a much cleaner form. The QSBT framework, even I have little idea what it does. It just combines everything together. So, any questions? Like, I think I finally managed to finish on time. Yeah. Any questions? Like, I have 5 minutes, I think, before like Sham is supposed to give. No, no, Q. It's not a special case. It is a much more general. So, as I discussed, unitary operations are rotation operations, right? And as we had the intuition that quantum walks are structured in a particular way, which is corresponding to task one, right? So qubitization basically does task one in a more efficient way. You can put this into a quantum walk framework. Yeah, yeah. So the structure in the unitary is it's a Zagedi walk operator. So go for Sham's like lectures. Huh. Of Zagedi walk operator. So like look at those, try to make the connection. Here U does not have any structure imposed, but just because you're imposing a structure does not mean a restriction because these are all unitary operations, right? So one form is actually equivalent to another form. So it's not a smaller class of unitaries. Yeah. Because given like the unitary, you can always convert it into that form of unitary. So yeah. Any other questions? So I my email ID is shared with everyone, right? So if you have any questions, just feel free to write me an email. Okay. Thank you. Yeah. Yeah. Thanks. I'll probably, yeah, yeah, yeah. Ah, yeah. I think I'll sit here. Yeah. Hmm. Yeah. Yeah. Oh, I think you will be needing something that I have. Huh? This? Okay. Yeah, yeah, Zoom is here. What is the yesterday's link? Share this. Is the recording still going on or you have stopped? Ah, yeah.